Alright, so this is section 4.5. So today is going to be the last day we practice sketching this, but you're going to be sketching for a very long time anyways after this. So this is called curve sketching because we are going to sketch out whatever the curve or the equation of looks like. We're going to draw out that curve. And pretty much you have been learning all of these things since Algebra 2, and we're just putting more and more precise things in there so you can draw the graph better. Okay, so guidelines. First one, you want to find the domain, whatever the domain is. X is not equal to, X is greater than, something like that. So just write out your domain. Second, intercepts. You got to have the x-intercept, that is when y is 0, and then y-intercept, which is when x is 0. Okay, so on the questions last night, there might be some intercepts that's hard to find. Then I would just skip it because you don't want to spend a lot of time trying to find an intercept. The whole idea is just, can you sketch this graph? You don't have to find all the parts if you already know how the graph should look like. Okay, so these are just guidelines. You don't have to do all of them if you know how some of them already looks like. Okay, C, symmetry. So you want to check the symmetry. Is it even? Even means f of x equals f of negative x. So if you put a negative x in there, will it look just like the original function? Is it odd? Meaning f of negative x is equal to negative f of x. Oops, sorry. Meaning if you turn this graph around 180, will it look exactly the same? And then the third one is periodic. Periodic only happens in trig functions. So that means f of x is equal to f of x plus k, meaning like if you add a phase shift to it, will it look exactly the same? Like sine looks just like cosine if you do a phase shift. Okay, so those are the symmetries that you want to look for.
So for the odd, we flip it over the x-axis or the y-axis?
No, flip over the origin, 180. Right, so just turn it around 180. Does it look exactly the same? Asymptotes. We have horizontal asymptote. If it's just polynomial over polynomial, just do what you did in Algebra 2. Is it bigger on the bottom, bigger on the top? Is it the same? But if it's not, which is why we need kind of calculus to help us know this a little better. The real definition of horizontal asymptote is, what does the function look like when x is going to infinity? Does it go to a straight line? Or when it goes to negative infinity, does it go to a straight line? So you're going to use limit in calculus to figure out the horizontal asymptote because we're not always going to look at polynomial. Sometimes we'll look at e to the x. Sometimes we'll look at natural log. And you cannot check the degrees. So you have to use limit. Okay, vertical asymptote. Vertical asymptote, the real definition is limit as x goes to a number from the plus side. Does this function go to plus or minus infinity? So does it shoot up and down, meaning it's undefined? Same thing when x is going to a from the left side. Does it go to plus or minus infinity, meaning it's undefined? So when the graph is going to a from the left side, does it just go all the way up or all the way down? That's going to be a vertical asymptote. Okay, third one, slant asymptote. So you had some slant asymptote on the homework last night. Slant asymptote is when the degree on the top is bigger than the bottom, you're going to have a slant. So for example, if you have 3x cubed over maybe x minus 1, you're going to do a long division and check the quotient. So you can do a long division, but this one is easier to do with synthetic division. So you can just do this. And then check the quotient. So 3, 3, 3, 3, 3, 3, 3. Okay, 3x squared plus 3x plus 3 is the slant asymptote. So basically, when you're graphing it, there is a parabola that's like an asymptote. Okay, so this quotient part is the asymptote, the slant asymptote. Slant asymptote means it's kind of tilted, like it's not a straight line, this horizontal line. It's not a horizontal line, it's either like a slant, like a linear one, or this one is a parabola one. So it's the graph is going towards a parabola, like it's skewing towards the parabola. So that's how you find a slant asymptote to make your graph more precise. Okay, be careful of holes. Holes sometimes happen. How do you create holes? Or how does holes happen?
The denominator, when the denominator equals 0, that's a hole.
Not necessarily.
When the denominator is canceled out by the numerator.
Yes, when the denominator and the numerator cancel out because they both equal 0. For example, if you have an x plus 1 times x plus 2 over x plus 1, this is going to cancel. That's going to create a hole. Okay, be careful of holes because we always forget that it's a hole, not a vertical asymptote. All right. Next. Now this is all calculus part. Increasing, decreasing. Okay, that has to do with f prime. So you want to first check what makes it 0 or does not exist. That's going to give you the critical points. Okay, you're going to find the critical points. Then you're going to create a sign chart. So, a f prime sign chart. You're looking for increasing, decreasing. That means you're looking for the signs on the sign chart. If it's plus sign, it's increasing. If it's negative sign, it's decreasing. Okay, so let's just write it down. Increasing means f prime is positive. Decreasing means f prime is negative. And just a reminder, critical points are what makes f prime 0 or undefined. Okay, if it's undefined, you still have to put it on the sign chart. Okay, next, local maximum. We want to make sure we can find the local maximum. Local maximum, again, has to do with f prime. 0 or does not exist. So check your critical points. Local max. How can you tell whether a critical point is a local max? Sign chart, what are you looking for? Change from what to what?
Negative to plus, plus to negative.
Positive to negative. Positive to negative has to increase and then decrease. So f prime changes from positive to negative. Well, there's another thing we can do. We can check double prime. We can check the second derivative. If you check the second derivative, you're checking for concavity, right? What makes it a maximum? When the concavity is what? Down, negative, yes. So when second derivative is negative at that point. At that critical point, if second derivative is concave down, it has to be a local max because the shape, right? You guys all look half dead. Okay. Local min. F prime changes from where to where?
Are you saying?
Negative to be positive.
Yeah, negative to positive.
Is-
可以啊，的话是
Yeah, is it and like f prime changes
no,
to negative?
either or. Because if it satisfies the first one, it will satisfy the second one.
Okay.
So just, you can check either one.
So is it like how do you find the point?
The point is when first derivative is 0 or undefined.
No, it's f double prime.
F double
How do you find
prime.
the point given that?
Yeah. So you take the equation, find the second derivative, and then take that critical point and plug it in.
Oh, okay.
Yeah, and you plug it in if the number is less than 0, then that is a concave down. So at that point, it has to be a maximum.
Okay.
Okay. Or the second thing you can do to check local min is f double prime. F double prime has to be concave up. If it concaves up, that point has to be a minimum. All right, the last thing we're going to do is just concavity and POI, point of inflection. Okay, first of all, check second derivative. We want it to be 0 or does not exist. However, what defines a point of inflection? Is it just if it's 0 or undefined? Sign has to change. Okay, so these are possible point of inflection. They are not the point of inflection because by definition, point of inflection is when f double prime sign changes. Okay, so first of all, you take the second derivative, make it equal to 0 or undefined. Find those points. Draw out your sign chart out. Only the ones that change signs are point of inflection. If it doesn't change sign, it is not a point of inflection. It's just where the second derivative is 0 or undefined. And then concavity. All right, so concave up. Concave up is when second derivative is what? Positive. So concave down, negative. All right, so A through G, that's all you need to graph any kind of curve. Of course, again, you might not need all of them. You might need some of them to draw a nice graph. So we are just going to practice for the rest of the class. Okay, so I'm going to give you another graph, and you and your partner have to graph it together. If you are both stuck, let me know.